Yes, it's a pleasure to have Ami again, Amihay Hanany from Imperial, giving us the fifth lecture of the lecture series on symplectic singularities, computational methods on symplectic singularities, right? So please go ahead, Ami.
Thank you very much. Today I will talk about brain systems. This is for theories with atypical charges. We start with it's a type 2 configuration in 9+1 dimension. There are various brains. The first one will be the Newell-Schwarz 5 brain. And we will set it to be along directions. I'll draw that's the common thing that people do. They draw all space-time directions. And they give the directions where the 5 brain is located. So it fills the first 5 directions and it's point like in the remaining 4. So this will be the NS5. We will have a D5 brain. And this fills these directions. It's again a 5 brain, 5 space 1 time, but it fills different directions. Both of them are point like in 6. And a 3 brain. And this one fills D5, D3, and it fills the same directions here. All of them share those directions, and it's over here. I will use colors to make it easy to identify. So I need 3 of them.
Yeah. 3 colors?
3 colors. Let's decide how you think. Let's see. Yeah, all of them are visible. So let's just make a choice. So we will have this color like that, and this and this. To make the distinction between those 3 different types. And the next thing I need is boundary conditions, how brains can end on brains. So I could have a yellow brain, it can end on red. And this is a projection. It's a 2-dimensional projection of this 10-dimensional space-time, where the direction here can be 6, and here the direction can be any of 3, 4, and 5. Right, so since on the board we can only draw the 2-dimensional projection, we to draw projection in order to understand how the brains behave, but we could use different projections each time at different two-dimensional projection in order to understand the corresponding grid system. Now, so this is a typical configuration, and this is a three-brain which is stretched between an S-brains. It can end on them. The other configuration will be this one. Could also end on D5. And now the two-dimensional projection is along 6.
Yellow, that's D3 or D5?
You see, it's here 3, 5, and S. Those are the types, and those are the colors. So this direction, the vertical here is any of 7, 8, and 9. Like that. Now, we could also have a three-brain which ends one side on blue, the other side on red. So it would look like this. And like that, right? Because now the projection is like this one, 6 and 3, 4, 5. However, if I look at it from the other way, then it would look like this. And it's the same brain system, but projected along other directions. Okay. Any questions? So now, next thing is to get the quiver. There are two types: electric and magnetic. The electric quiver is what I get when D3 between and S. It also uses colors. So magnetic would be D3 between D5. Right, so I could change those colors. So in order to read the quiver, what I need to do is to break the brains. So for example, here's a process that I can have. Suppose that I have a brain like this, and 2, 3 brains, one ends on the right and the other one ends on the left. I could move them vertically and get them to another configuration where it looks like this. Once it is like this, I can pull them apart. There are other directions. So in this case, here's a projection along 3, 4, 5. So I could pull them apart along 7, 8, 9. Okay. And this there will be a new distance, which is the distance between them. This is going to be a modulus for the corresponding quiver field. So those are the allowed processes. Brains can end on brains, so yellow brains can end on either blue or red, but not the opposite. Red cannot end on yellow. In any case, 3 brains can end on 5 brains, but not the opposite. Now, another comment, I could have other configurations. So I could do NS5 DP and DP, let's say DP plus 2 DP. So in terms of this configuration, I will add one direction here and one direction here. So that would correspond to P equals to 4 or 5 or 6. And for us, the interesting part would be between 3 and 6. Okay. So when I write type 2, it could be either type 2A or type 2B, depending on whether P is even or not. Okay. And the corresponding field theory is all of those theories have 8 supercharges, but they will be in P dimensions. How do I think about it? So this is a 3 brane. It has 4-dimensional space-time. 3 of the directions are common to all. So this is going to be the field theory I'm going to be interested in. The remaining direction, 6, is finite. So I'm going to take the approximation where this is an interval. I do Fourier expansion. I think of it as like in wave mechanics. I have infinitely many modes subject to those boundary conditions, and I only restrict to the 0 modes along the 6 direction, right? So there is a Fourier expansion, and we just forget about all other modes. The modes have a mass which is proportional to the 1 over the distance. And so I need that the distance will be sufficiently small. Okay. So this is the configuration. We will talk about the case P equals to 3 here. But we could, the other cases, 4, 5, and 6 are very interesting, and they bring new physics in each case. Okay. So we need to read the quiver. So we will give some rules. So if I have 2 NS branes and a collection of 3 branes between them, and let's say that there are k of them, it will be a quiver that has node k. Okay. I could also have another configuration. Let's add it to the same picture. Let's suppose that there are n D5 brains. So this will add to the quiver a framing.
That's UK.
UK with n flavors. I could also draw the same picture and replace red by blue, blue by red. It will be on a different projection. The quiver will be the same. I will just call it electric or magnetic.
You can draw it.
You want to go? So let's do another one. And then it's the same quiver. Electric, magnetic.
It's the identical quiver, but the brain could
Not just tilted, it's just two different types of weights. You could move from here to here by applying S dual, if you are in type 2B. But I don't want to commit to where I am. Right? So, in fact, I should fix this thing to say dp and this will also be dp. Here it will remain ns, but this will be dp plus 2. And again, I will call each type, the dp between ns will be electric, dp between dp plus 2 will be magnetic.
There's a question in the audience. Could the two NS5 bits be ended by the D3 and intersection at infinity?
What is the what configuration is it?
Could
We
be
want me to do?
You can
We can do many things. But yeah, the rules are quite simple. We have the rule of brain ending on brain. This side, right? And brains can reconnect. We will also need the brain creation. And brain creation, you could see here, if I change the order, right? So in direction 6, there is a clear order. This is in a position which is bigger than this one, because both of them are point-like in 6. And that's the only direction where both of them are point-like. So there is only one direction in 6 where there is an order. We call this situation that the brains are linked. And whenever there is a clear order, I could rearrange the order. So I could move this one to the other side, and then I'll get such a configuration. And now, if I move from here to here, there is brain creation. If I move from here to here, there is brain annihilation. Okay? So that's one of the effects which happens when I deal with such brain systems. So I have to take this into account. If I don't take it into account, I make a mistake. Then I could get wrong results. So it's like a computation. Working with brains is like a computation. Just need to be careful about the rules, the very simple set of rules. And if you are careful about all of the rules, then your computation is correct. Here's another quiver we can write down. Let's say we'll take two of them. And two notes. I have 3 NS brains. I can stretch 2 families. And let's call this K2 and K1. And for this, I will write a quiver, electric quiver, K1, K2. So the new thing which is added is this edge along an S plane. If I have K2 on one side, K1 on the other, there is a corresponding edge in the quiver. Similarly, over here, the edge here between a square and a circle corresponds to the fact that the blue are in the same segment as the edge. I could also add a collection of objects here, and this will correspond in the electric quiver N1. Any questions? Modular space. So the modular space here, every quiver has 2 modular spaces. Coulomb one or alternatively, we should call it the modular space of vector multiplication. Or the Higgs branch. The modular space of hypermultiplets. What is this modular space? It's the set of all possible configurations that I can have for 3 brains to be in between 5 brains. So here, if we look at the yellow brain, it's this one. It has 3 transverse directions, 3, 4, 5, and another 3, 7, 8, 9. They are the positions that the yellow brains can admit. Now, if you look at 3 between an S, like in here, it's fixed to where the NS is located. So no moduli here. But I have moduli here. These could vary, but these are fixed. So the opposite. These are fixed, those vary. So the 3 brains can be anywhere. And this is a 0 force situation because of the supersymmetry. It can be anywhere, therefore I have a configuration, a new configuration for a choice of a position in 3, 4, 5 that I set for the brains. So the vector multiplet moduli space depends on the dimension. It will be 6, 5, 4, and 3. And I'll have 0, 1, 2, and 3. That will be here actually it's becoming 4. Moduli per these three branes, these key branes. Any questions? This Higgs branch does not depend on the dimension, so it's always 4 moduli. The 3 moduli, let's look at this thing here. So I have 3 moduli, 7, 8, 9. And there's one more modulus which comes from the fact that I'm on an interval. So 4 moduli per brane, giving me a symplectic singularity. So if P is equal to 3 Coulomb branch, the symplectic singularity, and the Higgs branch is always. Any questions? So the symplectic singularity will be given, let's think about this. So if I change P, we said we fill along these directions, either 3 or 4 or 5. Right, so if I fill just in 3 and leave these, then this will be D4, D6. And then the next one will be D5, D7, and D6, D8. But in all of those cases, the DP brane will be fixed in 7, 8, 9, and the DP plus 2 brane will span 7, 8, 9. So I have moduli. And those moduli will parameterize the Higgs branch in this case. Let's see the how we move from. Let's draw a simple configuration. So let's take the following configuration. Actually, I want to start with the nest. That's the more conventional. And here 1 and 2. So I have 2d5, 2ns. It's symmetric. So what kind of configurations can I get from this? I could align the 2 d5 branes and also with the d2 brane. So it would look like this. The distance here will be the effective mass of the corresponding hypermultiplet. And the position of this guy is the bare mass, and the position of this guy is the vacuum expectation value of the scalar. So I could align all of them like this. Once I align, I could use the rule that I have over here. I can break the three brane and they can end. So now I will move to a picture. I will draw the same thing, but when in a different projection. When I do the same projection, it would look like this. Now, those are extended, and these are point-like. And there is a three brane which comes across like that. Now I have three segments. There will be three segments here, three segments here. The same brane system, just a different projection. I could now move this. I could move this, and move this. So I'll get a configuration which looks like this. I also change the relative distance. So I could have this one, and I could move the red, let's say, to this position, and to this position. So the three segments that I have are now in a different case. One thing which is important to notice is that in order to move this segment, I must move the position of the red brane. I cannot do it without, otherwise I'll break supersymmetry. This one is free to move, irrespective of the positions of those two outside. It's free to move. This is a modulus. This one is a special case because it's fixed to the position of the blue one along the directions where it is fixed, 3, 4, 5. It's also fixed to the directions of the red one, which are 7, 8, 9. So it's not moving. It's just fixed between the two. On the other hand, this one is can be anywhere, up and down. So that's the moduli space, the fact that this can be anywhere. Okay. The electric weaver, we said the electric weaver is a three brane between an S point. It's this piece. Here I will draw this weaver 1 and 2. Let's now use the brane creation mechanism. Here, I move it to the other side. So I could take this one inwards, this one inwards. And it would look like this. Here and here. Now I get the magnetic weaver because the conditions for the magnetic weaver are satisfied. I have the free brane between the D5 instead of the NS. Here it's between the NS. I make a set of transitions and I move to the case where they are between the D5. And now I have an electric weaver, a magnetic weaver. 1, 2. I picked an example which is self-dual. The electric and magnetic quivers of the same brane system are the same. Let's take an example where they are not. So let's just add one more. Let's take this.
But yet, in this example, is the case where the Higgs bunch and the Coulomb bunch map to each other.
Yeah.
The last lecture, you saw You ask whether it's a coincidence.
Now I realize it's not outside.
It's the conflict. It's linked by the bridge.
So let's take an example where the electric quiver and magnetic quiver are different. And just to emphasize, all of those 5 configurations are just different configurations of the same brain system. So let's add one more. Like that, and they can be anywhere. So I do the same procedure. I first align them, so they will become like this. And when I did this, I had 3 segments. Now I have 4 segments. 1, 2, 3, 4. And I can draw this along a different projection. So let's just expand it and draw and already break. So I do several steps together. Each 4 segment is different. These 2 are fixed, they have no moduli, and the ones in between have moduli. And the 3rd step is to do the, let me do it below here. I'll use the brain creation effect, and I'll move this one inside and this one inside. So I'll get a guy here, and 2. Okay. The electric quiver starts as 1, 3. And the magnetic quiver is 1, 1, 1, and 1. Any questions?
You do 1, 2.
It could happen that I'm not able to move from an electric phase to a magnetic phase. That could happen, and then I will not have it. So here's an example. If you take this system, let's just draw an example where such a thing happens. Take this. This will be now some monopole models. Like this. I don't even have, you wanted 1, I have 0. No defined. So definitely there's only one phase. Yeah, there will be many such cases where I cannot move to the other phase, and then I will get just one quiver and not both. Now there is a computational problem to figure out. So I could say some few words about this. If I think about, let's take such a system. And I stretch brains. And I have K1, 2, 3. The red brains form, when they are on top of each other, they will form the brain system of A3, the algebra A3, U4. So when they are all together, I have a U4. The quiver will look like K1, K2, and K3. K1. Like this. But I could interpret them as, so in physics, we call a brane which is stretched, like here, this thing here. This is the Hooft Polyakov monopole. There is a corresponding differential equation called the monopole equation. And what I have here is a U2 spontaneously broken to U1 squared. The overall U1 can be taken out, so it could be also written as an SU2 broken down to U1. The vacuum expectation value is the distance between them. So that's the breaking. And the solution, the monopole solution, is given by a three brane which is stretched between them. This is the Hooft Polyakov monopole solution. It's correct here and it's correct here as long as both of those are codimension 3. So only for the case of 3 and 5. This is a monopole solution, this is a monopole solution. If I have 4 and 6, then 4 between NS is no longer the monopole solution, but 4 between 6 is a monopole solution. Any questions? So as a result,
There's a question in the Zoom audience. How do you find the mass parameters and the variables parameters from the boundary equation?
you have so I use them implicitly without talking about them. So each time I draw a brane system, I make sure to scatter the positions. The reds can be anywhere, the blue can be anywhere. And so those positions of blue are masses. And positions of red are parallelepipeds. So, but if we vary the dimensions, for example, if this is a D6 brane and this is a D4 brane, the position now is 2 real dimensional. If it's 3 and 5, it's 3 real dimensional. If it's 4 and 6, it's 2 real dimensional. So the masses are only can be complexified, and there will be only complex parameters. And if it's 5 and 7, it's 1 real parameter for the masses. On the other hand, Fayet-Lopoulos terms are always positions along 7, 8, 9, irrespective of the choice here. So Fayet-Lopoulos terms, Higgs functions will always have triplets of deformation parameters. Any questions? So let's just finish here. Here it's the moduli space. That's something that Kim-Yong Lee from KIAS who had spent a lot of time. He developed a very nice theory from studying this thing that I'm going to write down, moduli space of monopoles, SU4 monopoles, of charge K1 for the first root, first simple root, K2 for the second simple root, and K3 for the third simple root. Also, Kilgene was involved in these works. And then I could map, right? So the Coulomb branch of such a system of this quiver, the Coulomb branch of this quiver is the moduli space of SU4 monopoles with charges K1, K2, K3. So if I know anything about this side, I could talk about the Coulomb branch, and if I know anything about the Coulomb branch, I can talk about the moduli space. More questions? So now I'm going to begin to erase. We can also do a non-abelian configuration because it's slightly confusing. If you haven't tried, you might get confused when you do this case. So let's do the case 2 and 4. The electric quiver is 2 and 4. Okay. Now, in this situation, the yellow brains are between red, but not between blue. How do I move to a situation where all brains are between blue, but not red? So I'll do several steps. First of all, I'll draw I'll switch orientation, and actually I'm going to do several steps together. So if it's too fast, let me know. I extend them. Here they are next to each other. I extend. I put one brain here and one brain here. So it's a collection of steps. I need to add another rule that I will say for the first time today, that when I have such a system, the number of D3 is either 0 or 1. Cannot be more than 1.
What is the origin?
Supersymmetry. If it's more than 1, supersymmetry is broken. So, what? 0 supersymmetry?
Yeah.
No supersymmetry at all. It's just if this configuration D5 and S K D3 breaks or K greater than 1 completely breaks supersymmetry. You could try and compute the vacuum energy, which is going to be non-zero. So I have to avoid such things, right? Because I'm looking for supersymmetric configurations. I'm after symplectic singularities. Symplectic singularities are what I'm looking for when I keep supersymmetry. So when I have here, I have 2 brains ending on the NS. So when one brane ends like that on this one, the other one cannot end again. It will break supersymmetry, so it has to end on the next one. Now, they are on top of each other. I exaggerate, I separate them just in order to see the effect. And this one on the other side, the same thing happens. This is fine, but the next one cannot end on it. It has to end on the next one. And now I'm left with more segments, right? Remember that there are many segments. This one will have 5 segments. This one will have another 5. Here we see 1. Here we see 2 of them combined together. 1, 2 combined together. I'm left with the following segments. 1 here, 2 here, and 1 here. Next effect, I bring the branes together inside. So I can use the brane creation annihilation mechanism. So I can move it here. The first brane will be annihilated. I move it to the next one. Second brane will be annihilated. So I'll end up here. Let me draw what I get. So the right one moves twice, it ends up here. The left one moves twice, ends up in the same place. And I'm left with these segments which are free to move. 1, 2, and 1. This is the final configuration. Now, all of the 3 branes are between the blue ones, and the red ones are free. They are don't have any branes attached. So I can use the rules for reading the magnetic quivers. 2 with 1, 2, 1 is framing 2. Now I can come up with a statement each branch of 2, 4 is the Coulomb branch of 1, 2, 1. And the Coulomb branch is the Higgs branch. But that's only correct in 2 + 1 dimension. This statement is called 3D mirror simple. Any question?
So you can verify it.
Yeah, so let me give you another description. So this one is the nilpotent orbit of SL4 with partition 2-2 closure. This is a quiver which was introduced by Kaff and Pochesi in the late 70s, and based on their prescription or explicit computation, you could just find that the corresponding symplectic singularity is this particular nilpotent orbit. And we could also describe it as a set of matrices.
How do I see it at SL4?
From here, the flavor symmetry is SL4.
Okay.
This is U2, SU4, we complexify. So it's the orbit of SL4. And the partition data is determined by those numbers.
You use a new notation.
For nilpotent orbits, what did I use last week? Minimal. Minimal is a very special orbit. It's the lowest dimensional orbit, which is non-trivial. The trivial orbit is just the point. Okay. 1 point, 0. And then the next one, which is non-trivial, is called the minimal orbit. Every algebra has one orbit, which is the minimal orbit. This one is not minimal. It's actually next to minimal. You could call it next to minimal instead. But in general, for A-type algebra or for classical algebras, orbits are denoted by partitions. You should have joined the discussion between these two because it was explained yesterday.
Yeah, I was looking around.
Yes. Okay, so that's the this side, Higgs branch and Coulomb branch. Right? It has a. So let's think of it from the point of view of the symplectic singularity. This is the closure of the orbit, and it has two ways. It could be a hyperkähler quotient. That's one construction. Another construction is as a Coulomb branch of some other quiver. And we give here the explicit form, and there are some combinatorial rules for computing it. So let's say I have the problem of starting with an orbit, so a partition. And given the partition, I can construct those quivers just by combinatorial techniques. It's straightforward.
Can I identify the partition from the quiver?
Yeah, so that's
the next step.
No, we could do that. It's not a problem, but it is a simple algorithm.
Maybe
It's written here. So here, for the Coulomb branch, those two appear with multiplicity 2. So I have position 2, flavor 2. And here I have 4 minus 2 is 2, and 2 minus 0, there's nothing, is again 2. So those are the two parts. Okay?
that's the simple.
It's a simple algorithm. It's a very, very simple. You teach a computer, and then you could generate all possible things. Very straightforward. So the Higgs branch was given by Kraft and Borchesi. They describe it late 70s. And the Coulomb branch was given sometime later. I don't know. And it follows some Langland's duality. There's a collection of things to discuss it. Yeah, so I wanted to write that this is the set of 4 by 4 matrices, which has 0 trace. They square to 0. And the rank is at most 2. If it was equal to 2, then this will be the orbit itself. But if it's at most 2, then I have 2 more orbits which are below, where the rank is either 0 or 1. So that's why it's the next to minimum, right? Because there are 2 orbits below. This has an explicit description. The Coulomb branch is a different description. It's harder to write it like that, so I will need to compute. I won't have it directly. Like nilpotent orbits are easy because it's very easy to write down the conditions that they satisfy. But for the Coulomb branch, it's called the Slodovy slice. S for Slodovy. Of Symplectic slice. Very good. Excellent. It's like, you know, when people came up with the name for MFIB, then there was a question, M for what? Could be mother, mystery. There were several other proposals. I don't remember. It's good. It's good. So So the slice, so that's a slice, which is, we will not have time to describe it. So it's a slice to the orbit 2, 2. It so happens that it's the same. That's an accident. 2, 2. Intersection with the nilpotent core of SL4. And I will just write it with partition over here like that. So it's not a slice, takes data of the 2 partitions. And in this case, we just specify them. I do not explain that, so I write it without explanation. Again, this is a fairly straightforward computation, that one. If you want to see the details, we can do that. It's not a problem, it just takes more time. It's all known, and it's quite well understood, certainly for data. When you deal with the other classical type, it becomes slightly more complicated. There are many involved issues that one has to consider. And for exceptional type, it becomes even harder. But many of those points are understood. On the other hand, some of the points are still under research. When Mitya comes, he's an expert in orbits and covers of orbits. So he could tell you a lot of stuff, even though he has not thought about it from the perspective of equipment. Okay, but he will tell you a lot of properties of the nilpotent orbits and slices and covers.
You can ask him.
Yeah, I don't know what he plans to talk about. You can look at his title and then see what he plans to do. Any questions? Okay, so now, given this set of moves, I have a whole class, A-type, of brain systems that I can compute once the electric quiver, once the magnetic. Okay? I will move to special effects in 5 dimensions. How much time do I have?
15 minutes.
50 minutes.
15.
Understood, yes. 50 would be too much. So let me erase this thing. Okay. Since we are doing with five dimensions, I'm going to put a brain here, and now make this D7. And D5. And I'm going to erase this stuff. Again, I'm going to write down 2-dimensional projections, but I don't have much of a choice. I have 5, 6, and I have 7, 8, 9, and 6. So let's take a simple configuration. Another complication which shows up is the following. Let's first understand this point. If I have a yellow guy which ends on a red one, now it's no longer red anymore. They mix together because both of them have the same dimension. This is a 5 brain, this is a 5 brain. So this is what we call brain web. In the mathematics literature, these are called tropical curves. Okay, so now we need to know a little bit of tropical geometry in order to understand 5-dimensional systems. And we will see symplectic singularities. There are still symplectic singularities, but when I draw the electric river, I will, first instance, I will not encounter symplectic singularity. Now the colors don't really have a meaning because those will combine into another one. Let's take this white color. And I will just have to specify that this is 1, 0. This is 0, 1. And this is 1, 1.
The PQ diagram.
And those numbers could be interpreted as the orientation of the line, the tropical curve, in the 2-dimensional plane. This 2-dimensional plane is 5 and 6. Okay, so this goes vertical, so I put 0, 1. This goes horizontal, I put 1, 0. I could also give an orientation. I could say that it orients in this way as 1, 0, or I can say it orients in the opposite way, but then I will write it as -1, 0. So the orientation reverses the chart. Now, if I add those two together, 0, 1 and 1, 0, I'll get 1, 1. And if I put orientation, so for this, the orientation will be like that. Both of them are incoming, this will be outgoing, 1, 1. So 1, 1, I could also replace by opposite orientation, but then it will be -1, -1. Okay? So those are the rules, and the same rules you will find with tropical curves. It's actually quite interesting because we use those brain waves before we knew what are brain waves, what are tropical curves. In fact, tropical geometry was developed, the big breakthrough came out in 2000. Our paper was in 97. So there was no way we could know about it because the breakthrough was later. But actually it took 4 or 5 years until I learned about tropical geometry, and then I realized that they are doing the same things that we do. So what they call a tropical curve is what we call brain wave. Okay, so let's draw a simple configuration. Remember that based on the previous rules that we had, if I take this system, I will get an electric river, which is just 2.
I mean, in some sense, this is what you call the tropical curve. It's related to the mirror curve.
You could assign a Newton polygon to this because you're on 2-dimensional plane. You could take the dual. Right, so I have the tropical curve is made out of lines and vertices. But lines also define faces. So I have 3 faces. So I can take the dual and I get a toric diagram. Right? I replace a face by a node, line by orthogonal line, and node by a face. So there's a 1-to-1 correspondence between brain wave or a tropical curve and the toric diagram. With toric diagrams, I only have the data of the way the objects relate to each other combinatorially. With the web, I have slightly more data because those have finite distance. This information is not encoded in the toric diagram. Any questions? So this is this is a correct configuration. This one needs to be modified because when I have yellow meeting red, it should be modified. This thing cannot be the same on each side. So let's modify it. And now, since there's no meaning to the colors anymore, I will draw it with white only.
Because of charge conservation.
Yeah, at each vertex there is going to be a charge conservation. And I will have, let's draw it in this way. Well, each line here is a 45 degree. And so you see that they satisfy. If I'll assign numbers, let's be slow here. And so let's say this is 1, 0. This is 1, 1. This is 0, 1. Wait, the conventional is, so this is 0, 1. 1, 0. 1, 0. So 1, 0 and 0, 1 come together and make 1, 1. And here I need that both of them will form. So I'll have a 1 and a -1. Am I right here? No, -1, 1. Minus. So when I add these and these two, it will give me this. And over here, it will be 1, -1, -1. Sorry. 1 and minus 1, 1. This is 0, 1. And indeed, if I, now we should be careful about the orientation, right? So 1, 0 is coming into here, but going out of here. So I need that this one, which has this orientation, minus this, gives me this. Okay. And this one will be -1, 1 with this orientation. So that's a very explicit way of depicting it. Normally, when you see such drawings, those charges are omitted. It's understood that there is some balance condition at each vertex. Sometimes it's we call it Kirchhoff. Kirchhoff.
Kirchhoff.
Kirchhoff. Yeah.
What is here?
Yeah. Kirchhoff. Church.
Yeah.
The church garden, church yard.
Yeah. Courtyard.
Courtyard of a church. Church courtyard. So you learn in high school. So it's the same thing. You have currents, and the sum of currents should be 0 at an intersection. And instead of currents, you use charges. Okay. Here's the brain system. And I cannot do much about that. This electric brain system will remain like that. But there's something special I can do. I have two moduli. I have the size here and the size here. I can take both of them to 0. This has an interpretation in the gauge theory. I will not explain it. So if I take both of them to 0, I get a configuration which looks like this. Now I can pull them apart. Only now. I cannot break this thing in a way which will preserve the topical curves. But if I set those two distances to 0, I now can pull them apart, and I have directions in 7, 8, 9. 7, 8, 9, remember what we said before, those are directions for the Higgs boson. I also cannot draw it in the 8, 9 directions, it will be difficult to draw. So just imagine that you could pull this out and leave this in. There's a distance between them, this will be a Higgs function. Next thing I will do is to compute the magnetic quiver. Magnetic quiver is, as I said before, D5 between D7. I don't have D7 so far, so let's add them. At the end of each one, a D7, this D7, as you could see here, is point-like in 5 and 6. So in this picture, it's going to be point-like. And as we had the rules here, 5 brane can end on a 7 brane. So I'll add a 7 brane. The typical notation is to put a circle. The 5 brane which ends on a 7 brane. And now I could see a moduli. I can pull this apart. I can pull this apart. I have 2 positions. And so I have 2 objects. With each one is an individual one. So that's the magnetic quiver. But I need to figure out how many times they meet each other. Intersection number. Its intersection number is 2.
So either the type 1 diagonal.
So I draw the 1, 1, 1, minus 1. I take the determinant. Okay. This is the magnetic quiver for this configuration. What do I learn? That the Coulomb branch C2 mod Z2. So for the 5-dimensional gauge theory, if I start with this quiver, there's no Higgs branch unless I set the moduli to 0, and then the Higgs branch becomes C2 mod Z2. Let's do another example, simple example. Let's take this case. This is the starting point. And I have K of them. And now I need to make it a brainwave or a topical curve. So I need to follow the intersections at each point here. So for the case of Seong, this is going to be kind of a messy thing. I might make a mistake. We could start. So here there is a correspondence with toric diagram. The corresponding toric diagram will be a collection of points on a line. So that will be the dual of this. And then I have, I could put one dot here corresponding to this guy, and another dot, let's put it on the other side, so that I will form a parallel graph.
That's not the unique choice.
Yeah, so I could put this anywhere here, and this will correspond in the gauge theory to a choice of a Chern-Simons level. So a gauge theory with K, SUK, will have K plus 1 choices for the level, and that will be the K plus 1 choices for the total data.
If that's encoded in the brain.
Yeah, in the brain web, it will be, so if we do, let's say the case K equals to 3, I could have such a configuration. Like this. That's one case. So that's for 3, K equals to 3. Or I can have, I can fix this one, and I can change the way this one is treated. So there'll be several cases. Now, let me take the case where the configuration is such that this line is parallel to this line. There's one out of many cases where this line would be parallel to this, and this line parallel to this. I think it will look like two inverted trapezoids. Let me see if I can draw it. Ah, no, it's here, no. Rak, what are you doing? Here's the parallel case. So K equals to 3, that's the parallel case. Right, so this is parallel to this, and this one is parallel to this. Now again, I have several moduli. I have the distance here between those two, another distance, that's 2, and I have this distance. If I set all of them to 0, 3 parameters set to 0, so you could think of it as the moduli of the tropical curve. It's a 3 real-dimensional parameter space. At the origin, I'll get this system. And this one. All moduli are set to 0. I want to compute the magnetic quiver, right? In this situation, here I couldn't fit to subwebs. If I ask what are the subwebs, there's only one subweb. But when I reach the origin, there is one subweb, and this can now move away, and this one will stay. There are 2 subwebs, so the magnetic quiver is going to be 1, and 3. I could also end with those 7 plates as we had the previous case. Okay, so this is the magnetic quiver, and here I can compute the symplectic singularity. And in general, if I replace 3 by k, then I will get k. The Coulomb branch is no longer a symplectic singularity. It's a real.
Yeah.
Oh, I see. I use the monopole formula. I think of it as just any other quivers.
You cannot compare. You don't compare from the figure.
In the figure, I'll be able to see that there are 3 moduli between them. There's one more which is coming from the fact that they are infinite each other. So not so much. The only thing I will see is this intersection number, which kind of a sign is yeah. So the thing is that I didn't tell you this, but I don't particularly like the name Coulomb branch, even though now it's too late to change. It's very, very difficult to change. But the name for the Coulomb branch should be magnetic construction instead of electric construction. And because its Coulomb branch is very special to 3D n equals 4. But this system shows up in 5 dimensions. And it's the same quiver. So if I think instead of the symplectic singularity as the combinatorial data, the geometric space that I extract from the combinatorial data given by the quiver, and stop thinking of this as a Coulomb branch, magnetic construction. Sorry? So then the magnetic construction of this quiver is sitting on it. I don't like to call it Coulomb branch because in 5 dimensions, that's not going to be the Coulomb. So what I do really is I use the brain system to extract the combinatorial data. From then I continue like the way that compute it along your technique. You want to do Bullimore, all of the techniques which are used. The critical step is to extract the combinatorial data. Okay? So we could, it's time to finish? Okay, so let's finish. In general, you could entertain yourself with many brain systems, and you will have this problem starting from the electric brain system, finding all possible moduli, finding all cases where I could subdivide into subwebs. And for each subdivision like that, I could compute the corresponding magnetic field. So I'll have many moduli spaces which are encountered in one brain system. Thank you.
Thank you.